So I think I'm the last stop before the beer at Beer and Gear. So thank you everybody for staying. I hope some of you will stay just a bit longer. I wanted to talk a bit about some new activity that we're seeing in the industry around dense topologies and routing. And we know a bit about this because here at NANOG, I think we've spent quite a few years recently talking about leaf-spine data center design and routing in these types of environments. And most of that involves talking about BGP. But we're starting to see a bit more activity in the IETF around approaches that can potentially solve the leaf-spine scaling problem in a variety of different ways using different protocols or extensions to existing protocols. So first and foremost, these are my ideas and my opinions. Of course, I do represent Arista Networks, but if I come off a bit opinionated, those are my opinions and mine alone. So as I mentioned, the rise of the cloud really has changed some of the network dynamics and some of the network design patterns that we typically employ to build big networks. And in fact, the last time I spoke at NANOG was in 2002. That tells you where I've been. I've been a bit away for a while. And in 2002, we were talking about networks that look like something on the left. In fact, this picture is probably circa 2002. And it was a typical kind of sparse layer 2 topology. Maybe you can call it somewhat of a polygonal lattice or triangular lattice or something similar. And we weren't really concerned necessarily about how to do routing in that case because most of the routing protocols that we had, like IGPs in particular, ISIS and OSPF, were designed for this type of network. Today, however, we have these three-dimensional hierarchical CLO or CLOS, I'll use CLO, I think it's the proper pronunciation, type of topologies. And these topologies, for a variety of reasons that we'll explore in the next 20 or 30 minutes, don't necessarily lend themselves well to traditional IGP approaches. And so BGP has become a bit of a de facto protocol to use in these environments. However, as everybody I think here knows who's spent any time really doing configuration with BGP and ISIS or OSPF, there are differences and there is a bit of loss of information that makes some things that are part of networking, particularly in link state environments, useful. And we'll talk about that as well. As I mentioned, these traditional WANs have these designs that are kind of geared towards a specific type of topology. Largely this is driven by, if you think about a WAN, it's driven by where available fiber is and where the placement of routers would be, typically in like what we call NFL cities in many cases, big cities in the United States. Internationally, it could be large capital cities, et cetera. And the concerns that we typically have in that case are, not necessarily IGP scale, although they do play a role, those concerns, but more along the lines of things like RSVP-TE tunnel scale, like what does the midpoint state look like in the middle of a network? And that has led to new protocol development. LDP was, of course, used where scale of RSVP couldn't be tolerated or the lack of scale. And now segment routing affords us even more scale. In fact, segment routing and multicast protocol that you might be familiar with called BEER, bit indexed explicit replication, depend on the IGP, at least in the current instantiation. And we'll see that many technologies, of course, that you're probably familiar with also depend on having link state information, fast reroute being one of them. The point of this is that for the past 20 or so years, the IGPs that we've used and the design patterns that we've used have been sort of dictated by the topologies that we see in WANs. And when we start to build networks that are much denser in terms of their topology, how the links are organized and how the vertices or the nodes themselves are interconnected, we start to lose the ability to use the IGPs, and we'll talk about that in a minute. Just kind of reinforcing the point here, we have this notion of scale-out design that is largely kind of at least emerged in the sense of what it looks like to build a data center. So when we think about scale-out design, we typically think of data centers, we think of switches, we think of these sort of leaf-spine topologies that are interconnecting a large number of computers in what we'll call, let's say, warehouse scale or building scale data centers. But if you think about a network and you really extract the components of any type of network, especially a network with big routers in it, the components themselves are largely constructed in leaf-spine ways, topologies as well. So consider a modern modular routing system. You have some forwarding chips on the line cards and you have some fabric chips in some kind of fabric, and they're usually arranged in a CLO topology as well. And if you have a multi-chassis system, in many cases those are multi-stage CLO topologies. And those topologies, those routing systems, are typically interconnected using something like ISIS as a message passing protocol, and perhaps even BGP. And there's a bunch, I won't go through all the various implementations, but for those of you here who've spent any time talking to your vendors, you probably know who I'm talking about. So, what we do in those cases, we hide that topology inside the sheet metal, inside of the operating system, if you will, and it doesn't really get exposed externally. That's kind of nice and it's fun, but that's not really necessarily how networks are being built today. In fact, we have this, sort of expanding requirement for denser networks and denser graphs. The picture on the right here, it's a social network, but if you look at some of the internet geography out there, you'll see, internet topologies that are represented this way. And if you have a BGP topology like this, like the internet, it typically works just fine, because really what we have is a very large path vector protocol that diffuses updates throughout the internet, a variety of different loop prevention and other mechanisms to kind of keep it stable. But it doesn't admit itself well to topology dissemination. So things like inter-AS or even inter-area traffic engineering or resiliency mechanisms just really don't exist, because in order to use the technology that we have available today to kind of give us ourselves that capability, we need more links state information. So, BGP can be used to build very symmetric topologies at very high scale in data centers. It can be used, of course, to build the internet. But in order to provide that link state information that we like to have to be able to determine whether or not we can reroute traffic onto another link, for example, or onto a different part of the network, BGP just really doesn't suffice here. I don't know if anybody's ever tried to build an IGP out of BGP, but there's no real way to do it in an IBGP way, because every router has to sort of map every potential prefix using a bunch of different BGP route policy mechanisms to kind of get a sort of link state analog, if you will, to what you would try to do with something like OSPF or ISIS. The only real way you could use BGP as an IGP is if you put every router in its own AS. And in this case, you just kind of reduce it to like RIP version 4 with more than 16 hops. And that's not really something that we want to do. It just becomes a pure distance vector protocol in that way. So why can't we use an IGP to build a dense graph or a network of comprised of a dense graph? And the reason why, if we kind of look back at the scaling rules, and this has been a sort of subject of debate. I think there's probably been more talks at NANOG about IGPs and comparisons between OSPF and ISIS and how to scale them than almost any other topic outside of security. John Moy, who was the architect and author of OSPF protocol, at some point, I guess probably mid to late 90s, said no more than 50 routers in an area. That was kind of the first upper scaling limit. Then Dave Katz stood on a stage here at NANOG in 2000 and did his comparative anatomy and went through what he considered at the time to be the state of the art. And the kind of idea was that you don't want to dump a bunch of routes from the internet into your IGP. If you get 80,000 LSAs in OSPF because of the hard 30-minute or 60-minute refresh interval, typically triggered at 30 minutes, then you're looking at about 23 LSAs an LSA every 23 milliseconds, just constantly flooding through the network. So you sort of cosmic background radiation, if you will, of LSA updates. The biggest concern, though, that he pointed out was flooding. And the flooding concerns associated with dense topologies were first encountered in the mid-90s when core backbones were being built with ATM switches, and big networks like UUNet, et cetera, were interconnecting their routers across these frame relay and later ATM topologies in a full mesh. And you kind of turn on ISIS and you just melt down the network because of all the flooding load. So this unnecessary redundant flooding is a real problem. It's more a problem when the topology gets very dense. So we have now, we've blown away these scaling rules because we have networks we know that are single area or single level that have like 8,000 routers in them. So it's not the number of nodes and it's not the number of routes. It's the amount of unnecessary replication of information that causes the most pain in building large-scale IGPs. And if you think about a folded clo topology or leaf spine, it's a bipartite graph, which is effectively n squared in its order. It's m times n squared in terms of the flooding density, which is effectively the same as n squared when you're thinking in big O notation, which is like a full mesh. The problem is that you can't use mesh groups, which is a potential solution, that we talked about, or that Dave talked about in the original talk, and which is the approach that we used to solve the ISIS problem that I referred to in the ATM case. You can't use mesh groups as they were designed in a bipartite graph because of the spine layer sort of intersects. So it's not a perfect complete graph or a perfect full mesh. So since then, once that happened, and once we did mesh groups, and then once networks became more point-to-point, less virtualized across like a VC core, this concern kind of waned. And I'd be surprised if there are any mesh groups deployed today anymore, even though the mesh group capability came out in the 90s. So let me just remind everybody what I mean here when I talk about flooding, and I'll just kind of walk through this animation. This is a simple leaf spine, as you can see here. And if you get an LSA or an LSP coming in from the outside into a leaf, it gets flooded on all its available links except on the inbound link that it came in on, so it's split horizon. And then the spines in this case also flooded to all the available leaves except back to the original. But if you look right here, you can see right away that the 2 additional leaves are getting double copies of that LSA, and then, or LSP. And then you flood it back up, and then the spines get the same copy back again. And this kind of repeats effectively order m by n in this case. Or you could really just kind of reduce it down if you wanted to, just to like the number of spines squared. And so this is a bit of a problem, right? Because now we have extra processing. It would be better if we can reduce this down to a sort of order n type flooding by reducing or trimming the flooding topology. And so the way we can do that, there's a variety of mechanisms algorithmically that we'll talk about, but let's just imagine that we try to create, as a simpler example, something like almost like a Hamiltonian path, not in the combinatorial way, but just a path that kind of visits every node once, tries not to use the same links more than once. And in that kind of way, you can see that we can reduce the amount of redundant flooding down to none, right? We just don't have to redundantly flood at all. Now, of course, we want some redundancy because if we have a failure here, then we lose the flooding topology. And I should point out that when we talk about flooding topology here, I'm not talking about the forwarding topology. So going back to the mesh group example, imagine you have 100 nodes arranged in a full mesh. You only have effectively like a tree-like distribution mechanism, almost like a dual hub and spoke or something similar to the way a non-broadcast multi-access network would work, or something like this, where you have 2 routers that are sort of designated as flooders, and then they're the ones that are going to provide the flooding to the non-designated routers, and only that set of links are going to be used for flooding. It's the same case there, even though that any 2 nodes can communicate with each other in a data way, or in terms of data exchange. So the first thing I want to talk about here, because I'm going to do a bit of a comparison. As I mentioned, there is interest here. There are actually a couple of different approaches. The one that I want to talk about most here is the one that keeps, or that maintains and solves just the flooding problem in the IGPs themselves. The other proposals involve using BGP in some way, or at least BGP mechanisms or ideas to solve the problem in concert with link state information. And just to foreshadow a little bit, they're called RIFT, Routing and Fat Trees, which is an IETF working group, so it's that big, that's at least that important to the IESG. Link state vector routing, which is also a working group now in the IETF. And then Open Fabric is the other one I was going to compare it to, which is a proposal from LinkedIn that leverages IGP with a couple of modifications. So as I mentioned, link state protocols are important in modern networks because in many cases we piggyback a lot of the capability that is available to us and that we leverage in modern networks on what is provided in the link state database. So if anybody here is familiar with RSVPTE, in order for us to be able to find like an explicit route through the network, we can't just know the nodes that we want to visit. We need to kind of know the links as well. If we want to do anything related to fast reroute, or if we want to prune the topology, or reserve bandwidth, or do some kind of link affinity or color preemption, all those things depend on extensions to the IGP that provide additional information about the link state in the network at a given time. So for example, if you want to do bandwidth reservations, you need to know how much available bandwidth is on a link, and that's not something you would get from a distance vector protocol. That's something that's part of the IGP. The same thing applies to segment routing. TILFA, for example, if anybody's familiar with topology independent link loop-free alternates, this requires a link state protocol as well. Bit index explicit replication, and so on. So, we've come to a point where, at least in WANs, it's really useful to have link state information. And it turns out that it's useful everywhere. It's just that in symmetric topologies, like a BGP leaf spine or a leaf spine topology, you don't really need much in terms of link state because you're load balancing across this ECMP fan out. But what happens when you leave that topology? So if you have a bunch of leaf spine data centers, typically they're interconnected across a WAN. And what happens is you may do BGP in the data center, and then you sort of run into a boundary router, which is like some kind of DCI router. And then that router runs an IGP and RSVPT and whatever across the WAN. So we have these like sort of network partition. And if we wanted to eliminate that partition, we could potentially avail ourselves of these link state benefits across a network that includes a leaf spine midpoint. So imagine a network that has a leaf spine on the left and a leaf spine on the right and a leaf spine in the middle. And you want to traffic engineer through that network. Well, it's kind of hard to do that if there's this big BGP black hole in the middle of it. And the only way that people get away with it today is by sort of creating a WAN between them all. And that WAN is effectively built using these principles. So what I'm proposing here is that perhaps we can have the best of both worlds. So Tony Lee, who's here somewhere, I don't know if there he is, Tony's right over there. I think everybody knows who Tony is. Tony has put forth over the past couple of months some ideas to solve this flooding problem. Is the first of the problems that I think that needs to be solved here. And he's put some drafts out there that I'll share. And in fact, you could see the references to the draft on the previous slide or the slide before the reference slide. The idea here is that again, the flooding algorithm is the piece that causes us the most pain in a dense topology. So why not fix the flooding algorithm? If we could fix the flooding algorithm, we can sort of fix this problem ultimately. And this is almost like an upgrade to the IGPs. So we want to reduce the redundant messaging, and we want to provide dense, scalable, rapid convergence. So same capabilities we have today. We don't want to kind of inhibit or in any way sort of handicap the protocol. It should work the same as it does today, but in dense topologies as well as sparse topologies. So what we're looking for is a flooding topology, like I showed before, that's a subset of the forwarding topology that's redundant, but it is minimal as possible. And so how do we do that? Well, we should look at some requirements first. The first thing we should do is it should be dynamic, right? This should be some flooding topology that some network administrator arbitrarily sets on the network, because if that's the case, then it won't be resilient around failures. We should be able to converge much faster than we would without the flooding topology. And so just to kind of give you an idea, imagine if you have a traditional flooding environment with lots of replication and unnecessary replication. You might say to yourself, well, it's not that big of a deal. You have a bunch of LSAs or LSPs in the queue. You look at it, you look at the sequence number, it's the same, no change, just throw it away. But there could be thousands of them, and there could be useful information buried in the back of the queue that is useful or necessary to converge around another failure. So you're sitting there just processing this queue, and I don't care about it, I don't care about it, yep, saw that, and you're just going and going, and finally like, oh wow, there's a failure somewhere else. We might need an SPF at this point. Or there's a new change in the reserved bandwidth on a link, and I need to trigger a CSPF computation and find better path through the network. And you can imagine how many different ways this can go. So we want to be able to make it so that it improves convergence, at least to the same degree that you would get in a non-dense topology or in a sparser topology. It should address a variety of dense topologies, not just leaf spine, not just by part type, but you can imagine there's different topologies available to you. Imagine if you extend the concept of a folded clo topology across a wider area, and you make the links a little bit more sparse just to save costs, or perhaps there's just no available transport. Well, now you don't have the same topologies you had before, so it can't be fixed to the topology. And there should be no single point of failure. Okay, so if we lose part of the flooding topology, we should be able to flood across a sort of backup, if you will, of the flooding topology. So we want to make that bi-connected. And we should also point out, and I mentioned this before in my example where you had a leaf spine topology in the middle of the network, that it should work outside of just the dense topology. So if you have, in this case, an IGP that floods across the topology, the leaf spine or the dense topology, whatever it may be, it should also be able to take information outside of it. So you can, again, using my example, transit through these leaf spine topologies. So just a bit more on how this works. Dynamically, the proposal is to elect an area leader, and this is similar to the way you would do like a designated router election. There's no magic here or mystery. And that area leader is going to create the flooding topology. So first it comes online, it knows what the physical topology of the network is at boot up. This may be a little bit painful as we get the network sort of stabilized and quiescent, but once the flooding topology is flooded, everybody will use that topology. So this is sort of distributed as part of the link state database update. And once everybody has the flooding topology, they can use it going forward. And since it's computed prior to any topology changes, it doesn't factor, it doesn't change the convergence time for the forwarding topology. So you can still forward across, you're still going to change and run SPFs as needed around failures, but you don't have to necessarily worry about how much that impacts the network convergence around a change in the flooding topology, because the only real change in the forwarding topology is that particular link on the flooding topology. We've done some simulation around this, and as you can see on the bottom, it's probably hard for, especially in the back, for people to see it, but on the sort of on the x-axis, we have the number of leaves in an environment. It goes from 10 to 2,000 on the left and 2,000 on the right. And then on the y-axis, so I'm looking at z being the vertical axis. On the y-axis, we have the number of spines, and that goes up to 32. And on the z-axis, we have the percentage improvement. That would be the reduction in flooding. And as you can kind of tell, the further up and right you go, or the denser the network is, the more leaves and spines, the greater the improvement, to the point where we get over 90% improvement in most cases. And that's that sort of brown region in this three-dimensional surface topology, or surface graph. So what we're seeing here is that if you have a low number of spines, then there's very little improvement necessarily. It's like half improvement. Sort of like the number of spines, the square root of the number of spines is effectively the improvement. But as we increase the number of spines and the number of leaves, then we really get a lot of improvement. And a 32 spine, 2,000 leaf data center, in a single stage that might be a bit unusual, but multi-stage it's not. And so this is a realistic improvement in convergence. Now there's two other enhancements I want to talk about. One is area abstraction. In the leaf spine topology, if you envision like ISIS with level 1 and level 2, and the leaf spine itself is in an area, and we make that a level 1 area, then any traffic that comes through it, particularly if the leaves are the ones that are connected to other parts of the network, traffic that's level 2 in that case can't traverse the level 1 area. The way we get around this is by putting links in that level 1 area as part of level 2 as well. So ISIS is a little funky in that regard. What we can do in this case, instead of putting every link in level 2, which would just make it one giant area and we would lose any area hierarchy, is to sort of abstract the whole level itself, the whole leaf spine, into a single node. And then the only links that really emanate from that single node are the links leaving that leaf spine. So what this looks like is something like this. So if you can envision this as a big network with a bunch of leaf spines, and if you can zoom in here and see this a little bit better, you can tell right here that we have 3 different areas. I don't know if this is working, so I'm just going to use my hand. We have a sort of a leaf spine here, a leaf spine there, and a leaf spine there. And these are the sort of 2-stage, in this case it's a 3-stage because it's folded. And then you add the second stage above, and that's another area. And the inter-area links are level 2. But if we treat the whole thing as a composite level 2 area, any links that leave that area, we can make even a higher level in the abstraction. So this is an ability that is kind of unique to ISIS. OSPF doesn't have this capability. ISIS, the spec itself, the original specification, had a field for the area or the level identifier that 2 bits were used and 6 bits were reserved. So we can exploit those bits and get 8 levels of hierarchy. And if you look at what I mean in terms of the abstraction, imagine a network like this where we have level 1 and level 2, and the purplish line indicates where the level 2 routing is, and that's the inter-area routing traditionally. But as you can see, because we only have level 1 adjacencies subtending off that, if one of those purple links fails, traffic can't traverse down to a sort of edge box and back up. And this is kind of part of the design of ISIS. The only solution in this case is to make all those links level 2 as well, which makes this one giant area, if you will, at least one giant link state topology. So we get no scale benefit. So what we propose is abstract this whole thing externally. So it looks something like this, like a router. And so every router outside of that area sees only a router. But internally, what we do is just use some kind of sort of full mesh tunneling mechanism to get the traffic across the network without injecting the links into level 2. So one proposal for this would be use segment routing and then treat all the segment routing links as effectively level 2 forwarding adjacencies. So they don't get plugged into the IGP, but we can still use them to flood across or to forward traffic across the area down to what would traditionally be a level 1 link and back up to the level 2 routed and out of the area. The abstraction continues, so from level 3 nodes outside of this particular area, all you see is a router with 2 links. So routers on the other side of the network, even though there could be 1,000 or 10,000 routers in this level 2 and level 1 leaf spine topology, the rest of the network doesn't see them. They just see effectively a pseudonode. We call it a supernode, but that's the thinking, that's the idea. So just to summarize before I get into the last bits in the comparison, if the point in ISIS dynamic flooding and area abstraction and hierarchy is to kind of upgrade the IGPs to the needs of the 21st century without changing them. And so there's a sort of a parsimonious approach at play here where we're thinking, we could sort of reinvent the protocols, kind of, work around the design issues. We have new design requirements, there's new topologies. But the protocols have served us well. We've kind of been endowed as an industry with these protocols that are, sort of almost, not that they're bug proof, but we understand them so well that we've been able to, sort of exploit them. I mean, think about BGP. It's been used for so many different things at this point. It's almost overused. I mean, you could use it now to like distribute stock information if you wanted to. I mean, it'd probably be a little slow, but just keep piggybacking information, and it's a great information distribution protocol. So, but it's a bit overloaded. And the IGPs also have been around quite a while. So let's exploit them. So let me just briefly talk, I'm going to high-level overview the other ones just to give people a little bit of comparison, and then we'll do a bit of summary. So Rift, the idea here is effectively, sort of the opposite of what I just said, which is, the network has changed, the design requirements are different, so maybe we should design new protocols. And the thinking in Rift, without going into detail because we don't have much time, and because this has been covered in other NANOGs, is to use link state information or link state approaches to flood information up the hierarchy, but use distance vector or diffusing methods to push information back down the hierarchy. So it's like, you want the link state information from the leaves to kind of percolate up, but you don't want it to keep bouncing up and down, between all these various leaf spine links. So you kind of percolate it up, but if it has to go back down, you just send a distance vector update. So that's kind of the general idea. There's much more to Rift. I don't want to give Rift short shrift, and I didn't mean to do that, but it's the only word that came to mind. But there's something to be said about what this protocol is aiming to do. The only thing is, it's kind of a new protocol and there's some complexity associated with it. However, there's enough industry interest that we have a working group that's working on it. So it's something to keep an eye on. Link state vector routing is another approach that leverages BGP link state. So we have this extension to BGP, an address family that carries link state information. And instead of just using that for topology dissemination for like a PCE or traffic engineering controller, why not actually trigger SPFs and change the BGP decision process to leverage the new routing information that comes from that SPF. So this is a slightly modified version of BGP, and so therefore it's a hybrid kind of protocol as well, even though it kind of aims to use BGP as the information carriage mechanism. Now I'd note that what's interesting about LSVR, maybe principally, is that kind of, because there's a lot of BGP already deployed in leaf spine topologies, that a sort of upgrade to to BGP could be useful if you want that link state information to be part of BGP. And then the last one I wanted to just briefly talk about is OpenFabric. OpenFabric is similar in some ways to what we're aiming to do with dynamic flooding and area abstraction, but it's a little bit less ambitious. It's really focused only on leaf spine. It's kind of like use ISIS to just kind of discover the topology, trim out some stuff that you don't need, add a few things that might be useful to kind of make sure that you optimize the flooding, and overall just don't really go too much further than that because it's really focused on a specific use case. So if you to compare them, what you kind of get is this sense that first and foremost, link state information is kind of really interesting to people. I mean, it's becoming more and more clear that the migration to BGP as a de facto IGP and leaf spine topologies has left us wanting, at least in terms of some of the information that used to be available. And so now people are starting to look at ways to find that information again. Now, this is not always the case. Obviously, there's huge leaf spine data centers all over the world. Everybody's using them to store their pictures and all these other things that we do now on our phones. But there is sort of more to be done here. There are more networks that are building leaf spine topologies. You're starting to see more things like mobile edge compute and sort of more carrier-oriented networks that are building leaf spine for data center, but they also want that link state information for routing and traffic engineering and things like that. So this is on the rise, and this is not going to go away. Scale-out design principles are becoming more attractive. You're seeing opportunities to build networks that don't involve investing in big multi-chassis systems. You're already getting this notion just from the fact that the cloud scale guys are building networks out of leaf spine because there is no other thing they can use, right? You could build 100,000 port routers out of leaf spine, or at least they're not routers per se, but they are interconnection networks that scale well beyond any known router today and any router that's on the drawing board. So there is something to be said about this scaling capability, but there is a deficiency when you lose that information, especially for carrier requirements. So you want to keep it simple. In closing, just a quick comparison. I won't go too much detail here. We have 4 different protocols. This is totally subjective. I said beer and gear debate fodder because this is just my interpretation of what's available. But if you think about, it's all IETF in terms of standards development. Rift is like a hybrid distance vector link state rather. OpenFabric, I would call a modified link state protocol because we're kind of pulling stuff out and changing some of the base capability, the base semantics of the protocol. So it kind of changes it. You can't use it outside of there's some restrictions on how it can be used, so we'll call it modified. LSVR is also a hybrid distance vector and link state protocol. It's a little bit less so. It's more of like a distance vector protocol with a link state decision process. It's hard to kind of really categorize these. And then finally, the IGP dynamic work that Tony's doing, I would consider that to be like an extended link state protocol. It's just you're extending the protocol, and this is semantic. You can argue that's extended versus modified. There's probably not much difference there, but it's one of those things where if you add some TLVs and turn on a couple of features, no one would have said that mesh groups changed the semantics of ISIS. It just changed the flooding topology. In fact, at least in terms of dynamic flooding, you're really talking about dynamic mesh groups. Instead of them being statically configured, you're discovering them or you're algorithmically computing the flooding topology. In terms of scale, it's hard to say what Rift's scale would be because it's such a different protocol, and I assume it's high, but it's still kind of unknown because as you can see, the other ones, we kind of know how they scale in terms of their protocol semantics. Rift is a little bit unknown at this point. OpenFabric, I think, is pretty medium in terms of scale, just simply because it only works in one topology. I think that LSVR is probably high. Mileage will vary depending on how much link state information and how you do that computation and how it impacts BGP, but considering it's BGP driven, we can assume it to be high. And I think that IGP dynamic is very high, at least in terms of what we're trying to do here because of the area abstraction. Now this may make people's heads explode, but imagine that you can take 10 to the third routers in an area, and we add 8 levels, in this case, to ISIS. Then you get 10 to the third to the 8th potential nodes that you can build in a single ISIS domain, let's call it. And that's 10 to the 24th routers. That's a lot, right? So I don't know if anyone ever built that, but at least theoretically, that's the scale. In terms of complexity, well, first in terms of config, Rift has a lot of autonomic configuration. There's a lot of a lot of methods and mechanisms that it aims to kind of simplify the configuration. I don't know if that changes how complex it is, but let's assume it's just as complex as autonomic networking is. There's some configuration, there's a lot of automatic stuff. Who knows how it'll work? OpenFabric's pretty light config. You presumably just kind of turn it on, say it's leaf spine, it's OpenFabric, and you don't have to do much else. Link state vector routing is still BGP, so you're kind of have the same configuration complexity as you've always had. And IGP dynamic, I think, is pretty light as well, because in this case, again, you turn it on, you do some configuration to kind of enable the capability. And it's still early, but at least in my thinking, it shouldn't be too much complexity there. The top 3 protocols are all CLO oriented, so leaf spine. And then in the case of dynamic, it's kind of any topology. You can argue that LSVR probably can work outside of a leaf spine topology, and maybe even in any BGP topology, but that's not where it's intended to do right now. And then finally, the complexity. I would think that when you change a protocol, it's going to be at least initially complex because people don't understand it. So I'll put Rift in that category. OpenFabric's probably low. People understand ISIS, so it doesn't really change much. It's not adding too much new capability. It's kind of pulling stuff out, if anything. LSVR, probably medium in terms of complexity, just by the nature of changing the decision process. I think that adds potentially some risk, and you have to kind of re-understand the protocol. And IGP dynamic, I could say medium there simply because it depends on how far you go with it. But if you start doing multiple levels and start abstracting areas, there's some things that you'll have to do to kind of make that work. And so there is a bit of complexity there. And then the flooding topology and understanding that in a dynamic environment may take some thinking. So, we'll give it a medium. There's a couple other approaches. I'll close with this. There's a lot of new interest here. So there's going to be, if there's money to be made, people are going to pile on, right? The ONF, the Open Networking Forum, has this project called Trellis that uses ONOS, I think, to kind of lay out the forwarding topology in a leaf spine without any routing protocols at all. So there's that, plus any number of different approaches that are being proposed. The only thing I would say is that, and this is kind of where I am generally, I mean, it's 10 years now since SDN really came on the scene, and there's still a lot of work that's happening there, and I think there's starting to be some good work. But we as an industry have been endowed with this really tremendous technology that at this point is as good as it gets. And with, if you've seen how much we've been able to do to extend the lives of these protocols, BGP particularly, but even ISIS and OSPF after all these years, I mean, these protocols are almost 30 years old. And they're still running the whole internet. So it's kind of like, why not use them? I mean, even if you don't want to use a commercial version, and there's an argument that could be made that BGP came into prominence in leaf spine in part because of white box and open systems and not a lot of availability of really solid commercial implementations. So BGP, Bird and Quagga and Go BGP and all these other BGP, there's just 40 different BGP implementations nowadays. This became easier, it's scriptable and all these other things. But now, you're starting to get some pretty solid ISIS implementations out there. And, this is a standard protocol, so take advantage of it. So one other thing I wanted to talk about, and I'm just going to throw this out here because it's starting to hear some grumbling about it. There are other topologies that are coming from the high-performance computing industry that have people thinking, especially in financial services where latency is really critical, because some of the new topologies can reduce the hop count and the latency of a network. And they're a bit exotic, but they're not leaf spine. And so if protocols to scale leaf spine networks are the ones that are on offer, what if they don't, what if you don't have a leaf spine topology? Now, I'm not saying that anybody's building anything like this, but it's something to think about as you start. If you're going to build a new protocol, I think it should be able to work in a lot of different environments. And that's one of the nice things about IGPs that we have, and even BGP. It's sort of topology. Both of them are pretty much topology independent. We've seen this. We've made them work in multiple different environments. So just to conclude, if the goal is to leverage and gain link state information, perhaps it's worth just fixing the link state protocols so that they flood better. And if you like BGP because you either have it or you want some policy control or whatever BGP does well, then perhaps it's better to do BGP instead. Any questions?
Okay. Thank you very much. We're out of time.
There we go.